Hello and good morning. This is Craig Kozeminski with your experiment number 6 pre-lab video. As a short note of review from experiment number 5, I want to encourage you all to make sure that you go back before this week's lab and rehearse some of the calculations that you did in preparation for this week's lab quiz. Specifically, can you equate the heat energy gained and the heat energy lost? So in our last experiment, we know that the water was gaining heat energy and that the metal cylinders were losing heat energy. In that experiment, we were able to set these two terms equal to one another, as evidenced in step number 10 from the previous experiment, where the negative heat energy gained was set equal to the positive heat energy lost. And this allowed us to rearrange these equations to solve for the heat capacity of the metal. In advance of this week's quiz, you should be able to do that calculation or that algebraic manipulation of that equation in order to successfully solve for the heat capacity. Now, for this week's experiment, experiment number 6, we will be looking at electrical energy conversions. And this is hopefully something that you've begun to review by this point. In this week's experiment, we have some new tools or instruments that we will be using in the lab. So first off, we will be using a power supply. And a power supply, as written in the lab introduction, is simply going to be the source of our electrical energy. And we'll be able to manipulate the power supply to approximate a certain number of volts that we are supplying to the system during our experiments. We'll also be using two digital multimeters, and one of the multimeters will be set to give us the current in units of milliamperes, and the other multimeter will be set to detect the actual voltage coming from the power supply. And so even though we will be adjusting the voltage on the power supply, we'll actually be relying on our digital multimeter to give us the most accurate and most precise readings of our actual voltage. In this experiment, there are two parts. In part A, we're going to be looking at the conversion of electrical energy to mechanical energy. And this is usually the point in the video where I say, if you have not done so yet, please pause the video and make sure that you've read through the entire introduction, procedure, lab report questions, data table, as well as the exercise worksheet before proceeding any further. But generally speaking, what we're going to be looking at is the conversion of energy, electrical energy, from our power supply. These are our voltmeter and our ammeter, and these are both multimeters. And again, these are going to give us units of volts and milliamps moving from the power supply to our motor. And our motor is going to be connected to a weight plate, and we are going to make some observations about the amount of time that it takes for our motor to lift our plate a certain height. And these details are provided here in the setup and in the procedure. So please make sure you go through, as always, highlighting particular steps of the procedure that are very important. I'm going to make one highlight here. It's very important when using the motors that if the pan is not close to the floor, that we unwind the string until the bottom of the pan is within a few centimeters of the floor level. We do not want to rotate the motor against the direction in which it is designed to move, otherwise we could damage the motor. So in part A, again, we're going to be looking at the conversion of electrical energy to mechanical energy, and we'll be taking all kinds of measurements in order to do so. So we'll zoom down to our data table for part A. So in our part A, the electrical motor, you can see that we're going to be measuring the initial and final position. And we'll be recording this in centimeters and converting to meters. So of course, like always, we're going to make sure that we want to write that conversion down, 100 centimeters per 1 meter. We're going to determine the total height lifted in units of meters. We're going to be recording the mass of our object that is lifted in units of grams and converting it to kilograms. So as always, 1,000 grams equals 1 kilogram. The average voltage that occurs during the lift is simply going to be read off of the multimeter. The same is true for our average current. The time elapsed will be measured. Our velocity, as always, is going to be equal to our distance divided by time. And so what you want to make sure that you do here is that you're prepared to effectively do these calculations. So our electrical energy consumed is going to be calculated. You're going to want to record the equations here for electrical energy, potential energy, kinetic energy, work, and power. And then we're going to do this twice. So we're going to do it initially with an empty pan, and then we're going to do it 2 more times with a pan that is loaded with additional weights. And we're going to calculate the efficiency of our motor, which this equation is actually given to you here as being equal to work divided by the electrical energy times 100%. So let's go back up to part B. Too far. All right, in part B, we are going to be looking at the conversion of electrical energy, not to mechanical energy, but to heat energy. This part of the experiment is going to be somewhat similar to last week's experiment, where we are going to be adding an object to a calorimeter, and we are going to observe how that object increases the temperature of the water that is inside of it. And so, hopefully, you by this point you've read through Part B introduction and the procedure, and you're prepared to answer questions about that procedure on the online quiz. Again, we'll go down, we'll look at the data table for Part B, for Part B. So again, in a similar fashion, we're going to record the mass of the empty cup, the mass of the cup, and the water. This is going to allow us to calculate the mass of our water. We're going to record the initial and final temperature so that we can calculate the change in temperature. And in this instance, we're also going to record the amount of time. Now, this time is going to allow us to calculate our electrical energy. And we're going to compare our electrical energy to our heat energy gained by the water. And what this is going to do is it's going to give us an experimental ratio of electrical energy spent per heat energy gained by the system. And so that's what this unit is here. Joules per calorie is going to be a ratio of our electrical energy divided by our heat energy. Finally, in our exercise worksheet for this week's experiment, there are some assumptions that need to be made, so I want to quickly highlight those. In question number 1, it says an electrical resistance heater is used to heat 280 grams of water from 25 degrees Celsius to 85 degrees Celsius. Determine the heat energy gained by the water. And so if you're thinking, well, Mr. K, this looks like a very familiar question, you would be absolutely correct. You're going to calculate the heat energy, that's delta Q, gained by the water. And that equation should be known to you at this time. However, in question 2, it says calculate the time needed for the heater in question 1 to raise the temperature of the water if the heater is rated for 1,000 watts. And so one key assumption that needs to be made for this part of the experiment is that our our heat energy gained by the water in question number 1 is exactly equal to the electrical energy spent. Now, in order to solve this question correctly, however, you're going to have to convert your calorie answer of your heat energy gain to joules. And once you have your electrical energy in units of joules, you'll be able to calculate the time needed for the heater by using the equation that the electrical energy is equal to power times time. Now, the form of this equation that's given in your actual lab report is from the calculations page. It's equation number 5. And that equation is that power is equal to electrical energy divided by time. So for this question, question number 2, you're simply rearranging that equation to solve for t. And that's how you will end up that time is equal to the electrical energy in units of joules divided by the power in units of watts. Finally, in question number 3, it says a motor rated at 1,000 watts and 110 volts is run for the same amount of time as the heater in number 2. And so this is a bit of a hint that you're going to be using the time from question number 2 So your answer from 2 is going to be used in 3, and uses the same amount of energy. If the motor is perfectly efficient, calculate the height that the motor could lift a 120 kilogram mass up to. And so, what question 3 is actually asking you to do is to equate your electrical energy, which is equal to volts times current times time, to your potential energy, which is equal to mass times gravity times height. And in this equation, or in this problem, you'll be solving for height. Thank you. I hope you all have had a wonderful and restful weekend, and we are looking forward to seeing you this week for experiment number 6.